Hello, let's look at another challenge from ångstromCTF. This time it's a challenge called a Happy Family. It was actually a two-part challenge. One part was a pawning challenge and the other one was reverse engineering, and we'll look at the reverse engineering part in this video. We were given a source code, so that's is a bit easier. So let's see what we have in this challenge. So the file that we are given was called a Happy Family C file, and we can see there's some C code that we need to analyze and try to understand how we can get a flag for the reverse engineering part. This is the part from the pawning challenge, so we'll not look at this at the moment. And if we scroll a little bit down, it says, okay, so here it's a flag for the reverse engineering challenge. So we need to find out how to get to this part so that we can get a flag. Okay, but maybe first let's look at the whole source file. So we start with a main, which actually sets some buffering. It forks itself, and yeah, one part will be executing this child function and the other one will be executing a parent one, the parent one that we saw that there was a comment about the flag for the reverse engineering challenge. So let's look at this function parent for the moment. So we get some input with some constants ps. Okay, we have some string being printed. We get some input from the standard input. We check if the input is if it's not equal to this ps constant, then we'll just exit, and if it is, then we'll create two another buffers which are half of the size and half plus one, and then we will split the input into those two parts. So one would be I guess first half and the second half based on the position of the entry character. So if it's even or odd, it will be placed in one of those two buffers. Then we put a 0 at the end, and then we the open fifth, it's opening file. We'll write the second half to this file and we'll close it and we'll deal with this a bit later. But with the first half, we cast it as a unsigned long into the two numbers, and then another buffer C1 to C4, and we convert those numbers to strings. So this is the buffer 1, this is the buffer 2, and here is the buffer 3 and 4. So what are we actually doing here? So we pass n1, which is number 1 created from the first half, to this toBase method. And let's see what toBase actually is doing. And toBase, what name suggests, actually convert a value to a string representation of this number in a base. And in here, the base is actually 13. So this is the base, and we use only those characters as characters in our alphabet. So we have the ångstromCTF 20 as our digits in our base system. So if we pass a number, we will get some string that represent this number in base 13 by using those characters. You can see they are unique, so we can do that. Okay, so that's what we'll do with the n1. N2 will do the same, but we'll just negate all the bits before we do that. And N3 and N4, we don't know what is this. We have those here, but where do we get those values? We read them here, but from where? We again open the file, and this file that was mentioned here, and we read those two numbers to N3 and 4, and the same happens as here. So we convert to base, but N3 is we add the lead value, and with N4 we subtract hexadecimal 4242, and after we do that, so we convert those 4 numbers to string representation, we need to have them to be equal to those values that we see here. So C1 was here, has to be equal to this string. C2, which is negation of N2, has to be equal to this one. C3, which is here, has to be equal to this one, and C4, which is here, has to be equal to this one. Okay, so we know a little bit more. So if one of those will not be equal, we will, exit. So that's what we don't want to happen. We want to have them all match. Then we'll go here. And when we get those numbers and 1 and 2 and 3 and 4, we can do the reverse. So we can, from those halves, generate the input values. And the input is the actual flag which we need to enter here. So yeah, when we do that, we will know the flag. But I haven't mentioned yet about this file that going on here. So we write this second half to the file. But what's going on here? And actually, what's going on here is in the child. So in the child, we read those values, and we generate a salt from that, and this salt is being converted to N1 and 2. Also N1 is just negated, minus N1, and N2 is XORed with this 1 2 3 4 5 6 7 8 9 0 and all the letters in hexadecimal digits, and then we write to the file. So we need to include that in our solution, so that those files that are being read from the input are still converted with this conversion that we see here. So first value will be minus, and the other one will be XORed with this value. And then we write it to the file, and then the file is read here again, and we use those values that were generated in the child as N3 and N4 to generate C3 and C4. Okay, so how can we get the input so that when we apply those conversions, we'll get those strings? Well, we can use a Z3 solver. And this is what I did. So I have a Python script which actually uses Z3 to solve the problem that we need have in this challenge. So I'm creating 4 integers, of course the solver, and those are the solutions that we want to get. So N1, N2, N3, and N4, and I'm adding a constraint that N1 converted to Z3 at position I needs to be equal to position I in the solution. So each character has to be equal after conversion to Z3. I'm adding some additional constraints here. I will explain in a moment what's going on here. And then we check, okay, if it's solvable, we get the model, and then we extract the actual values. So we run eval on those variables, N1, N2, N3, and 4, and we do the operation that we saw in the binary, in the source code, in reverse. So the bit negation is the same. Here we have like we subtracting the lead value, and here we adding 42, 42, and XOR is of course reverse to itself. Then it's the same operation, and then we get the V values, which just for the sake of debugging, I'm printing here. And then having those V, we can convert them to the numbers and then to ASCII, and of course they will be in reverse because we have little endian. Then we have the 4 strings input, but then it's not yet over, because those strings were in the source code. We saw that it's being splitted. So basically here we have this 2 halves being created. So we also need to reverse that operation, and it's happening here. So we are reversing first half and the second half twice, and then if we have this array created, then we can just print the value. So maybe let's just look a little bit at more functions. So basically, to ASCII is just generating a character from the value and then reversing it. To base is basically the same as we saw in the source code. So we are dividing value by 13 and then taking a character, modulo 13. This is our base. 2 hex just converts a value to a hexadecimal, without the negative values. And add constraints I will explain later. And 2 base Z3 is just the same as 2 base, but written as a Z3 equation. I don't know if this could be simplified, this if ladder, but it was the simplest I could think of during the CTF. So basically, if the value is 0, then we'll return A. If the modulo 13 is 1, N, G, S, T. So basically the consecutive values in our alphabet, and then we call simplify to basically reduce, if it's possible, this equation, and we return it so the solver can work on it. Okay, so maybe about those add constraints. So this challenge has multiple solutions. Basically, there are multiple values that could be generated that satisfy those conditions. Maybe I missed something, but at least it was generating a bit of multiple results. So I needed to add some additional constraints that the value is not like the one I saw before. So here are those constraints added that, okay, we don't want to n1 to be this, n1 to be this, and n2 to have equal to be some of those values that I'm getting those results during runs. And I also added that it has to be a number between 0 and like max value that I can store. And with those additional constraints, we actually can retrieve the correct flag that will satisfy all those conditions. So let's see how does it run. If we run Python 3 in a happy family, it will wait a little bit, and then we get, okay, that the first part is this 1 underscore something, the second one is this, the third is this, fourth is this, and if we reverse the process of splitting those, we'll get a flag that says great parent with a better child, and we just need to put that within the competition, CTF competition name, and squarely brackets, and that's the flag. So that's it. I hope you like it. It was quite nice of usage of Z3 to solve a reverse engineering challenge, and if you like, please hit the like button and subscribe, and see you next time. Bye bye.